Thank you for joining the Astronomical Society of Tasmania. We are a community of space lovers, amateur astronomers, and curious minds, and we hope you enjoy this month's special presentation. Wishing you all clear skies.
In UK, so we haven't met. You've had a lovely conversation with Lisa for the last few minutes, but and we're glad that everything looks as though it's settled technology-wise. So once again, welcome. So Dr. Jenifer Millard is co-host of the Awesome Astronomy podcast. I did get onto that podcast this afternoon, and certainly we'll be going back. Plenty of energy in those podcasts, so well done to that. Jen is also managing director of the Sky Guide app, so some of you may have that app on your phone, and one of many apps, but certainly I'm trialing the pro version, so we'll see how we go with that.
Yeah. We've got some big updates coming very soon as well, so
okay, terrific. Jen is also co-organiser of Astro Camp UK, which is
we're much smaller. We're just we've been going for over a decade, but we're about 100 astronomers meeting twice a year. But there is an Astro Camp out in the States, and I think unfortunately we started at the same time, and so now we've both got the same name.
Oh, okay. Right.
Yeah.
Jen is also a science presenter on BBC One. Now, I don't believe that she has any spare time, but she says she enjoys practical astronomy, so that's terrific. Apparently with your dad, which is even better. Jen has a PhD in astrophysics from Cardiff University. Tonight, she will be presenting us with a snapshot of the very impressive Vera Rubin Observatory located in Chile, commissioned only last month. Already the images being recorded are amazing, and I'm sure astrophysicists around the world are just waiting to get all this information based on wide-field images of the southern sky, and to help, among other things, understand the vagaries of dark energy. I've always admired physicists to be able to, when they don't understand something, just put a dark in front of it, so that sort of gives it a label. So tonight's presentation will last from about 40 to 45 minutes, followed by questions. So please hold your questions until the end of Jenifer's presentation. So, Dr. Jenifer, we're really pleased to have you as our first international guest for the Astronomical Society of Tasmania.
I'm very excited too.
Very pleased you made the time to talk with us, and please give Dr. Jen a very warm welcome.
Okay, so I'm going to start the presentation, but once I start it, unfortunately, I lose the view of you guys. So yeah, just keep your questions until the end, just because unfortunately I'm not going to be able to see any hands going up. Right, we'll just, hopefully you can see that nice big slideshow now. Yeah, I'm taking the silence as a yes.
Yes, we can see it. So, Jenny.
All right, perfect. All right, let's get going. So yeah, thank you for that lovely introduction. You've covered most of what I've got on this Who Am I slide. But yeah, I completed my PhD in 2021. So I did it on the stuff between the stars. So this was about the evolution of the gas and dust content of galaxies over most of cosmic history. So I was essentially staring at a tiny patch of sky that you could sort of cover with a grain of sand held up on your fingertip at arm's length. But there was about 60,000 galaxies in this patch of sky, going back. And so that's what I was doing for my PhD, was seeing how their content changes over time, so we can understand how galaxies come to be in the wonderful variety that they are today. But while I was doing my PhD, I actually kind of realized that my true passion is actually talking about science and talking about the science I'm doing, but also what others are doing. And so this is what I do now, is I work in science communication. So yeah, most of my work is with Fifth Star Labs Sky Guide, so we're free to download on the Apple App Store. So there's my official blurb for them. Our logo's up in the top right corner. But yeah, I'm a BBC space expert. So you see me on like radio, TV, I'm on YouTube a bit sometimes as well with them. My most recent venture was looking at AI in astronomy. So that was quite fun. I'm happy to talk about that later as well. I think it's a really interesting topic. But yeah, as Ross was saying, when I do occasionally get some free time, it doesn't happen very often, but I like to build Lego. I recently completed Hey Hey from Moana. And I'm also owned by a cat, because you know how it goes with cats, right? So I thought in this talk today, we're going to explore the Vera C Rubin Observatory and also the woman for who it's named. Look at why it's in Chile, its science goals, its kind of main features. And I'm going to do it a little bit differently. Instead of just kind of like walking you through all the facts and figures, I was actually fortunate enough to visit the site myself in 2023. So I'm going to sort of give you that story, my perspective of what it's actually like to go to this gigantic observatory, and really try and give you a feel of what these observatories actually look like and how they work and how they're operated. So hopefully that'll be a little bit different. And of course, we'll explore some of those first images right at the end. So I think without any further ado, we should get going. And it's really interesting to try and start this talk because, we're sat here on a planet in the outer backwaters of a very average spiral galaxy, as someone once said. And yet, really, we shouldn't be here. Our home galaxy shouldn't be, and so then by extension, neither should we. So we live in what's known as a grand design spiral galaxy, and this is an artist's impression of our Milky Way, based on studies that have used long wavelength light to sort of peer through all of the optical light blocking dust and reveal what's hidden behind it. So here is an actual map of the structure of our galaxy conducted using 21 centimeter hydrogen radiation. And so what you're seeing here are the actual spiral arms and the spiral structure of our galaxy. That tiny little yellow arrow there, that's where we are. And so then we're looking out in this direction. And if you're wondering why there's this great big wedge of data missing, well, that's because the radiation can't quite penetrate the dense material at our galactic core. And so it casts a shadow. But it's based on, this is the very first survey that was done decades and decades ago. And so that's what this artist's impression is based on. And some of you may be Monty Python fans, and I am. You may remember the Galaxy song from one of their films. And, even like decades on, it's actually not far off in terms of the numbers that they quote in there. So our galaxy does indeed span some 100,000 light years side to side. And we sit about 2/3 of the way out from galactic center. So not in one of the two main spiral arms, but we sit here in what we call the Orion spur. So it's just this kind of little bit that comes off one of the main spiral arms of our galaxy. And we take about 230 million years or so to go around once. And so the last time we were in this part of our galactic neighborhood, dinosaurs were just starting to roam the Earth, which is mad. And that motion is the first line of evidence that we shouldn't be here, because we are moving too fast. If we look out of our galaxy, and you guys in the Southern Hemisphere, you have a much, much better view of our galaxy because you're looking towards the center of our galaxy. You can see way more stars than we can in the Northern Hemisphere. So I'm not jealous at all, no. But if you go to a dark sky site and you can see the plane of our galaxy. And if we look out into our galaxy and we trace the motion of stars and gas right at the edge of our galaxy, we do find that they are moving too fast. If we look at this plot on the left-hand side, we have this dotted line, this dashed line, and this is what we would expect for the speed of stars and gas and dust in our galaxy as we move out from galactic center. So galactic center is here, and then we move our way out, going further and further away, and we would expect the speed to drop off based on the amount of material that we can see, and so then the gravitational forces that can execute. But when we actually look at the data and we measure the stars and we measure the motion of the gas, this is what we find, that actually the speed is increasing. There is a huge discrepancy that the outer outskirts of our galaxy and also other galaxies are moving extraordinarily quickly compared to what they should be. And this red line I've added to the plot is roughly where we sit from the center of our galaxy. So we're moving much, much quicker than we actually should be. Our galaxy should literally be flinging itself apart because there isn't enough mass to create enough gravitational force to hold on to gas and stars that are moving at these great speeds. And yet, that's not happening. We're here. We are here in a galaxy that is absolutely not flinging itself apart because our solar system has been here for 4.5 billion years. And then there are also stars in our galaxy that are twice that age, even more. So our galaxy has been around for a very, very long time. Isn't that strange? And then we also have the fact that we are here at all. And by we, I don't just mean you and I in terms of life in the universe. I mean all of the stars out there, the gas that's out there, the planets, the galaxies. There should not be this much structure in the universe. It should not be possible to this level of richness. So this is a James Webb Space Telescope deep image of the night sky. And in here, almost every speck of light that you see is a galaxy. So this is a galaxy cluster. And this shouldn't exist based on the amount of stuff that we can measure, the stars that we can see, the gas that we can detect. There should not be this much structure. Because our current leading theory to sort of explain the formation and the evolution of the universe, or cosmology as we call it, is the Big Bang theory. And so it says approximately 13.8 billion years ago, our universe started from this incredibly dense and hot point, infinite density, infinite temperature, infinite pressure. And of course, there's no such thing as infinity. It's just code in physics for we don't know. This is where our theories break down. But this is our current best understanding of the evolution of the universe. And so 13.8 billion years ago, this point suddenly started expanding outwards rapidly, briefly faster than the speed of light. And that's a period that we call inflation. And so after inflation, you've got this kind of cosmic soup of material. There's no atoms. You've just got subatomic particles, which eventually form into things like protons and electrons. And they're all mixed up with photons of light. And in the period of inflation, where you're existing in a quantum realm, before you've got these particles and this cosmic soup, because it's a quantum realm, there are tiny random changes. There are tiny random effects. And when you then get particles starting to form, there are tiny regions which are slightly more dense and slightly less dense just by chance. And over time, these then are reflected as tiny temperature fluctuations in what we call the cosmic microwave background, which you can kind of see here, just after this infinitesimal point. So there's all these tiny fluctuations. The universe is expanding. There's regions which are slightly denser, so they are slightly warmer. There's regions which are slightly cooler. They're slightly less dense. And we can't actually see any of this cosmic soup. The universe is completely dark because all of the photons are trapped up in with all of the particles that are existing at this point. The temperatures are too hot for atoms to form, and so all photons are doing a ricocheting off all of the protons, electrons, things like that. There is no light free streaming through the universe. That means we cannot see it. So we will never be able to see this period before we have the release of the cosmic microwave background. It's all kind of trapped up. But as the universe is expanding over about 400,000 years, as it's expanding, it's starting to cool down, and eventually we get to a point where the first atoms can form. So it's mostly hydrogen, a little bit of helium, and then a little bit of lithium then as well. And so this is the release of the cosmic microwave background. This point here, 400,000 years or so after the Big Bang. And within the cosmic microwave background, which we can see here, and I'll just expand out for you now. So here is a map of the cosmic microwave background. So it's this oval shape, because you got to think of it like a big map of the sky that's been stretched out. So it's like when you see a big map of the world and it's like that oval shape. So it's a big map of the spherical sky and it's put out onto a 2D plane. So that's why it's this kind of oval shape. And so you've got reflected in the cosmic microwave background all of these tiny temperature variations, right? And these tiny temperature variations are reflecting those tiny density variations in the quantum realm of inflation and the period reflecting afterwards. Now, these temperature fluctuations that we see in the cosmic microwave background, that were imprinted on that moment when the light could first start free streaming, and it's reflecting where atoms were slightly denser and warmer, less dense, and then cooler. These temperature fluctuations are on the order of 1/100,000th of a degree, right? They are absolutely tiny. But based on the amount of material that there is out there that we can count in terms of stars and gas, there is not enough time, even with 14 billion years of cosmic history, there is not enough time for these tiny quantum fluctuations, which became density fluctuations, which we see reflected in the cosmic microwave background. There is not enough time for all of these tiny changes to manifest in all of the structure that we see today in the universe. They are too small. They're too small for matter to start aggregating once that light is free streaming through the universe, too small for it to start pooling and build up into galaxies and galaxy clusters that we see today. There must have been something else helping the normal matter, which we see in the right-hand side picture, pool together to be able to form the very first stars and galaxies. Something that we cannot see, that does not interact with light, that could start pooling in these tiny density fluctuations almost from the word go. That is one of our other lines of evidence for dark matter, because we know that dark matter doesn't interact with light. And so it could start pooling in these tiny, what were originally quantum fluctuations, which manifested into density variations. The dark matter can start pooling at these density fluctuations much, much earlier on. And so that means by the time the light is then free streaming through the universe, because the universe has cooled down enough for the first atoms to form, then the normal matter that you and I are made out of, and stars and gas and galaxies and planets and black holes, all of that normal matter has almost got a big head start for something for it to grab onto. And so the gathering of the material is greatly accelerated. And so you can actually start getting the structure that we see today in the universe, because the dark matter has already started pooling. It's made these great big gravitational wells, which the normal matter can fall into very, very quickly. And so these are the two main lines of evidence that we have that dark matter is out there. It exists. We have that large scale structure of the universe, because there's not enough time to grow galaxies and galaxy clusters without dark matter. And then also the fact that galaxies that we measure right throughout, different types throughout the universe, they are spinning faster at their outer edges than can be accounted for by the stars and the gas that we can see. And that is about as much as we know about dark matter. We know that it accounts for about 85% of the mass content of the universe, so the baryonic content. So we're ignoring dark energy at this point. We know that it helped forge the cosmos. It helped enable galaxies to exist. And we know that it's there because it's enabling the outer regions of galaxies to spin much quicker. It holds them together like glue, stops them flinging themselves apart. But it doesn't interact with light. We can only infer its presence through its gravitational influence. And yeah, that is it. That is what we know about dark matter. And, it really is a mystery. And as Ross was saying, astronomers will put the word dark in when we don't understand something. And that is it. That is what we know. But this is what the Vera C Rubin Observatory, one of its main science goals, is to tell us what dark matter actually is. And when it's making up, over a quarter of the matter energy content of the universe and 85% of all of the matter out there, it's pretty important that we do actually know what this stuff is. And in the foothills of the Chilean Andes is where we find this amazing observatory. It is gigantic in nature, and it's gigantic in ambition, and gigantic in name. It's an 8.4 meter telescope, and it's going to spend a decade mapping the entire available night sky in extraordinary detail. It has a 3,200 megapixel camera, which is the biggest digital camera that has ever been built and used for astronomy. I think it's actually the biggest digital camera that has ever been built, full stop, unless, there's something in the military that they're not telling us about, which would not surprise me. And it is going to generate 20 terabytes of data every single night. I think I worked it out, and it was something like the equivalent to 80 of my phone. I've got an iPhone, like 256 megabyte one, and it'll fill 80 of them every night with data. It's extraordinary. And it's going to capture the light from 20 billion galaxies spanning about 90% of the history of the cosmos. And this will give us the information to actually unlock the secret of how we came to be. So how all of the large-scale structure in the universe is here, how galaxies are not flinging themselves apart, and just what dark matter is. It is going to have an absolutely, timeless legacy. It will be legendary in the annals of astronomical history, right? Just as actually its namesake should be, right? You've probably heard of Edwin Hubble, like the Hubble Space Telescope, right? And you've heard of James Webb as the NASA administrator before we landed on the moon with Apollo. And so you've heard of the James Webb Space Telescope. And even though Vera Rubin provided the first undeniable evidence of dark matter's existence, she is really, she's just not well known at all. And this is because astronomy does have a horrible habit of hiding, pioneering women in its history. But that is starting to change. And we're seeing that by the fact that this observatory has been named after her. So it has helped cast her into the limelight where she rightly belongs. And it is a shame that, it took the naming of an observatory for her to be brought into the limelight. But I'm glad that it's happening now because she is a giant, just on scientific merit alone. And, she was a huge advocate for women as well in astronomy. I mean, she was active in a time where she would try and go to different observatories and use their facilities, and they would tell her that she couldn't go because there were no female toilets. And how dare she use the same toilet as a man? So just to kind of give you a bit of context of the sort of crazy battles that she was trying to fight just to do science. So I thought we'd talk a little bit about the woman herself, who has inspired the creation of this observatory. And then, of course, it's been very rightly named after her. So Vera Rubin, she had a tough childhood, she describes in several interviews, because the Great Depression of the 1930s, it hit her family hard. But even though it was tough, she said she's always said it was a very happy childhood. Her parents encouraged her natural inclination towards science. As a teenager, she went to the local astronomy club. She built her own telescope as well from a large cardboard tube with a lens on the end of it that she bought. So you can see that she's always had this fascination with the night sky and a real affinity for science. She went to Vassar College in New York, graduated in 1948 with her degree. She then went on to Cornell, did a master's degree, completed that in 1951, and then went off to Washington, finished her PhD in 1954, where she was looking at the distribution of galaxies in space and seeing how they tended to clump together and were not evenly distributed. And while she was doing all of these degrees, she also had 3 children. So she absolute madness, doing all of those degrees and having 3 children, raising a family at the same time. And you can see how determined and hardworking she really was. And then in 1965, she started working at the Carnegie Institution in Washington. And it was here that she started studying spiral galaxies. But her real big breakthroughs came when she started working with an instrument designer called Kent Ford. And in this picture, this is her a little bit later in life. And she's at the Kitt Peak Observatory at the 36-inch telescope. And around this time, we kind of have to get a bit of a perspective about what the general opinion is of dark matter at this time. So dark matter had been postulated. So Vera Rubin didn't come up with the idea of dark matter. That goes back to 1933 with this guy, Fritz Zwicky. And yes, he looks like he's got an attitude in that picture. And by all reports, he did have a stinking attitude, but brilliant scientist. So I guess that's a story of a lot of brilliant scientists, right? And Zwicky, back in the 1930s, he was studying the motion of galaxies in the Coma Cluster, which I got a picture of up at the top. And so he's looking at the Coma Cluster, and you can have a look at the Coma Cluster. I'm not sure if it's the right time of year for it, but it is. You can see some of these galaxies with backyard telescopes. And he was looking at the Coma Cluster, and he was doing something called the mass to light ratio. And the mass to light ratio is where you measure the mass from how galaxies are moving in a cluster, which you can estimate using spectroscopy, which we're going to come on to that in just a few slides about how you measure the motion of galaxies doing that. And so you measure the mass based on how galaxies are moving. And then also you measure the mass based on the amount of starlight, where, you say, well, most of the mass of a galaxy is locked up in the stars. I can see most of the stars. And so then you can get mass estimates. And it was always supposed to be a kind of like sanity check, because you had 2 different methods and they should give the same answer. But what he found actually was the mass that he estimated from all of their motions was much, much greater than the mass he could estimate from the starlight, from the amount of stars in the galaxy. And so he concluded that actually the galaxies in this cluster, they should be flying apart. They should not be sticking together in this group. And so he said there is something invisible that we cannot see that is binding these galaxies together. And he sort of coined it dark matter. And all the way up, as early as sort of 1962. So we've got to remember that, that this is a few years before Vera Rubin has joined the university. There are papers out there which are looking at the rotational speeds of galaxies, and they are noting that actually this rotational speed of galaxies is pretty much constant as you go out from the center. So that's what you get on the left-hand side in this animation. So in the left-hand side of this animation, we've got a spiral galaxy that's got lots of dark matter in it. That's what the purple pinky is representing in the heart of this. And then on the right-hand side, we've got how a galaxy would be moving if it didn't have lots of dark matter. And if you have a look at the outer edges of this galaxy, you can see that the stars are actually moving pretty slowly. It's pretty sedate. So this is what we would expect with no dark matter. But with the dark matter, you can see in comparison that the spiral arms, everything around the outer edge is moving really, really quickly in comparison. And so this is where we have, this constant speeds going out all the way out, whereas here it's dropping off because we don't have this extra dark matter speeding up the outer edges. And so this effect has kind of been noticed at the time, but it was very much poo-pooed. People were not believing it. They were not having it. They were saying, no, there's errors in the measurement. There's no way that these galaxies are moving that quickly in their outer edges. Don't be ridiculous. And so this is where Vera Rubin comes in. So she's at Carnegie. She's collaborating with Kent Ford. Kent Ford is known as an excellent instrument maker. Here they are installing a spectrograph onto a telescope. So you can see the telescope mirror, this like burgundy bit here, and then all of the camera system underneath here. And here is a spectrograph that's being installed, and a spectrograph splits up starlight, and we'll come on to that in a second. So she's working with Kent Ford, and they built this really, really sensitive spectrograph using magnetic techniques for focusing, all of the state-of-the-art equipment at the time. And they put it on the world's most powerful telescopes. And so it meant that they could then record these spectroscopic signatures of tiny portions of distant galaxies. Just like this. And when they were doing it, they studied about 60 different galaxies, and they found that it was conclusive that stars at the outer edge of these galaxies were moving really quickly, just as fast as those towards the center. This was not the laws of physics. This is not what should have been expected based on the amount of stuff in these galaxies that could be measured. They should have been flying apart. And so there has to be something holding them, and that is dark matter. So the way they do it is like this. So here we have a spiral galaxy up at the top. And if you take a spectrum of the galaxy, so this is where you look at the galaxy's light and you split that light up into a rainbow of colors. And you split it again, and you split it again, you split it again. You get it down to very, very fine wavelengths. So you're looking at, instead of all of the colors of the light, you're seeing exactly, specifically, which wavelengths of light are actually causing those colors. So instead of just sort of looking at the red part of the rainbow and looking at all of the red light, you've gone down to such fine detail that you can say to the wavelength exactly what light it is that you're detecting. So hydrogen is out at about 658 nanometers. And so you're looking at that hydrogen, because we know there's a lot of hydrogen gas in galaxies, and sort of saying, right, it's exactly this that's causing that color. You can look at oxygen as well. We see a lot of oxygen in galaxies, and you can look at that wavelength and see, like, this is exactly where the emission is. And so then once you've split your light out into lots and lots of different wavelengths, and so you're seeing, right, I've got a nice peak here, like we've got in the yellow at a very particular wavelength. This is where all the emission of light from this galaxy is coming at. That's when that light is absolutely stationary in the middle. So this galaxy isn't rotating in the middle. But then when you look at the part of the galaxy that's coming towards you, that light gets blue shifted. It gets shifted towards shorter wavelengths, towards the blue end of the spectrum. And the difference is what tells you how fast this galaxy is spinning. Because the quicker that stuff is coming towards you, the quicker that gas is coming towards you, the more blue shift you'll get. And equally, when you're looking at the part of the galaxy that's moving away from you, that light gets shifted towards longer wavelengths, towards the red end of the rainbow. It's very much like when you have police cars with sirens or ambulances, and they're driving towards you, and the pitch gets higher and higher and higher. And then as they go past you, the pitch drops off and it gets to a lower sound. Well, that's because As they're coming towards you, the sound waves are getting compressed. So the wavelength of the sound is shorter. So that would be the same as the blue. It's shorter wavelengths, and so it's more compressed. And then as they're moving away from you, the sound waves get spread out. They've got a longer wavelength. So that's the same as putting it towards the red end. And so it's just like that. And so the amount of shifting that you get, that tells you how fast it's moving. Because the faster it's moving, the more shift that you'll get. And of course, this is just a cartoon, right? So this is what it'll actually look like. This is an example in the near infrared. And this is just looking at a couple of stars, just as an example. So this is looking at Arcturus in the red, and then the sun spectrum is in the green. And here we've got some really strong emission lines here, which have been inverted in this plot. But as you can see, compared to the sun, the emission lines from Arcturus are moved, they're shifted to longer wavelengths. So they're red shifted down to the red end of the rainbow, down to longer wavelengths. And this tells us that Arcturus is actually moving away from the sun from our perspective. And what this actually looks like in terms of a galaxy is here we have a galaxy. I know it's a smudge, but believe me when I say it's a galaxy. So here we have a galaxy. You put your spectrograph along here. So it's going to take the light all along this line, split it up into really, 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 really fine wavelengths. And then here you can see we've got 3 emission lines. We've got a really strong line here. And then we got a weaker one here and an even weaker one there on the left-hand side. And you can see this is in the middle of the galaxy. So this is where the wavelength of light should be. This is where the wavelength of the light should be. And then as we move out, we go one side of the galaxy is going to longer wavelengths. And so that's moving away from us. And then we go to the other side of the galaxy. Here we are moving to the other side of the galaxy. And that's going to shorter wavelengths. And so this half of the galaxy is moving towards us. And this shift that we see away from the center line, which is here, this then tells you about the rotation of the galaxy. And her work, so this is what she essentially did for 60 galaxies. And she calculated that there was about an 80 to 20% ratio in terms of the actual matter that we can see making up a galaxy in terms of its stars and gas, and then the amount of invisible stuff out there. And she convinced the scientific community that this dark matter is real. And this is why she's always kind of contributed as kind of like the mother of dark matter, because although it wasn't her concept that she came up with, she undeniably proved it. And it was her work that she then inspired investigations into dark matter to happen, to continue. Because, you know, she saw something in the universe. It had been there all along. It had sort of been noted, but it really needed daring, determined, pioneering work to convince everyone. And this is what the Vera C Rubin Observatory is. It is daring, it is determined work, and it is absolutely pioneering. So we'll now explore the observatory itself. So this is one of my pictures from my trip. You can see that when I went a couple of years ago, they're still working on the construction of the site. Here's a crane. And just for a little bit perspective about how big this building is, that's a coach. And then these are all 4x4s. So it's an absolutely enormous building. The telescope is actually up here in this part of the dome. And then here we've got warm room and engineering, which I'll explain to you as we're going along. So how did my visit come about? Well, we were visiting another large telescope site, which is about 12 or 13 kilometers away from the Vera C Rubin as the crow flies. And this is a site where there's lots of telescopes and you can sort of rent time on them and things like that. And this was one that was under construction. So here we are, this is me, and then my 2 bosses, Chris and Nick, and we are Fifth Star Labs. And I realised that the Vera C Rubin was really close to us. And I thought, well, if we're in this neck of the woods anyway, why don't we try and go for a visit? And this is from that smaller telescope side. You can actually, that is the Vera C Rubin on the crest of the mountaintop. So you could see it from where we were. And then, I forget which ones these are. I think it's one of them Gemini South. Might be. Should have double checked. And it took a lot of organising, a very, very long email chain over months and months prior to our visit to arrange this trip, because they have to, check your passports and make sure you're a legitimate person, you're not going to be a danger to the scientific site and all of this. But eventually, we did get approved. And this is one of my favourite pictures that I took on the trip. And I think it really gives you an idea of what it's like there. So most of these pictures are either from a phone or from a DSLR. And the Vera C Rubin, it sits at the edge of the Atacama Desert in Chile, so one of the driest places on Earth. You can see that there's a few bits of scrub bush, and there's also a herd of goats at the small observatory that I was at, which I'm telling you now, when it's 3:00 in the morning and you've got 50 glowing eyes staring at you from the bushes, is more than a little bit terrifying. But it's very, very dry. And part of the reason that you want this is you want those cloudless skies, of course. But you don't want that moisture, so that you're not hitting the dew point and you have to kind of stop your observations as the temperatures drop and the nights roll on. Also, if you want to do infrared astronomy, water in our atmosphere is very good at absorbing infrared radiation. And so it means that if you're trying to look at objects in the infrared, because you want to look at maybe the dust that's in them, or you want to have a look at the gases, you want to look at the stars in the infrared, unless you get above most of the Earth's atmosphere and above those clouds, you're not actually going to detect the radiation from your objects, because the clouds and the water vapor has just absorbed it all. So that's another reason as well. You want nice stable atmospheres, which you get when you're really high up as well, up above as much of the atmosphere as possible. And we're talking about 2,500 meters up at this sort of altitude. So it's on the edge of where altitude does start becoming a problem in terms of motion, but it's not crippling. Not like when you go to Hawaii. It's extremely barren, as I hope you can kind of see, and it is just rolling hill after rolling hill after rolling hill, rocks, scrubland, that kind of thing. But it does mean you get absolutely extraordinary skies. So I hope this is coming out all right on the projector, but this is just like a 10-second photo that I took on my phone. And you can see extraordinary detail of the heart of the Milky Way, which I know you guys are all familiar with down there where you are in Tasmania, the coal sack, the Southern Cross, all of this. And it's just what we call science quality skies. Now, much like Vera Rubin's path to glory was tricky, the road to the observatory is extraordinarily rough. It's just dirt roads, as you can see, very sheer drops, which I hope this picture gives you an indication. When you're driving along, like the dust is just billowing, and you have to have a specially trained driver take you up to the observatory. You cannot just go up there yourself on your own accord. Although what I will say is that the roads for us to get to the smaller observatory, they were rougher. And we had to do those ourselves, but to get up to Vera Rubin, you have to go with a specially trained driver, which is why it takes a lot of organising to get up there. Here again, just to give you an impression of how dry it is, the sheer drops and everything, it's just dirt roads. But then, as you start climbing, there's a few subtle things that you notice as you're getting up to higher altitude. So the skies start to get darker. So you go from this like cartoon blue that you can kind of see right at the bottom of the hill to this really deep sapphire. And that is reflective of you getting higher up into the atmosphere. Also, you do notice the temperature starting to drop. So, you can see us when we're up there in pictures, we've got like coats and jumpers and stuff on, but we're there at the height of, within, you know, decent temperatures. And you also notice that your heart rate is increasing as well. And part of that is excitement, but part of that is because the air is getting thinner. And so, you know, your heart's starting to beat, and you do have to kind of watch out for your altitude sickness. But this is one of the first glimpses that you get as you're driving up to the observatory. And it's absolutely thrilling just to see this iconic kind of all of the angles on the building and everything. And then when you get up there, you kind of park outside and you have to be escorted in, so you can't wander off. You have to wait for someone to kind of come and get you. And this is the sort of sight that you're greeted with. And I've put this picture in to try and give you an impression of just how dominating this building is. So this is where the dome actually is. So this is where the telescope is. It's just this little bit up here. And then all of this is engineering, maintenance, and operations, because it's so high up on the mountain, you can't keep taking bits of this telescope down to work on it. So, for example, to clean the mirrors, right? You can't keep like chucking it up and down on these bumpy roads and everything. So you have to build the engineering building to like clean the mirrors, to resurface them, all of this. And then, of course, you have to do your operations as well. So when you get in, because it was still a building site, it was very much, you had to have really sturdy boots, and you had to put your hard hats on, your high-vis jackets, and you had to do your whole safety briefing as well. And so then the first place they take you to is the warm room, or the control deck. And, you know, because gone are the days where astronomers sit at the eyepiece. This doesn't happen anymore. Astronomers are controlling it from a very comfy, you know, climate-controlled room with huge banks of screens. I mean, these aren't even computer screens. These are ginormous HD TVs that they're using. And this is all in that kind of adjacent building. And you're monitoring things like the weather, the health of the telescope. Is it slewing at the speeds that you expect it to? Is it on the correct target? Is it in focus? Do it, you know, things like that, and making sure that it's progressing through its target list as it should be. Now, the Vera C Rubin is actually, a lot of it is operated using AI technologies. It will scan the entire available night sky every sort of 3 to 4 nights. And using artificial intelligence, it has this bespoke scheduler that has been built by astronomers, which factors in things like the moon phase, the wind direction and speed, atmospheric conditions, aeroplanes that are going to be flying overhead, any delays introduced through slewing and filter changes, to work out night by night the most optimal observing schedule to fulfill its general scanning goals of this, you know, night sky every 3 to 4 nights, and also then its specific research targets that it has to do as well. And it's all calculated sort of autonomously. Then once you've kind of explored the warm room, you head off into engineering and maintenance. This is one of the big engineering and maintenance hangars. So on the left-hand side, this huge silver thing, this is for resurfacing the mirror. This is a ginormous vacuum chamber, which is going to be used to resurface the mirror every few years to make sure it's detecting all of that light. And then the thing that's like a yellow circle down here, down on the right, this is the casing, the protective casing for the secondary mirror, which hadn't arrived yet when we were visiting. There's a support box to keep that in until they were ready to install it on the scope. And then this is just a view from the other side, and this enormous yellow cross that you can see here, this is a massive support platform for the primary mirror. So that's how they'll move that. They'll use this equipment to like move it off the telescope and then move it into the vacuum chamber for cleaning and then resurfacing as well. Just so that you can see, this is a picture from Vera Rubin, so not one of mine, but this was them then getting the secondary mirror into the support box later on, about a year after we were there. And then once you've gone through engineering, you then start making your way up to the dome, and it's very exciting because you're going through, it's all kind of exposed metal work, grating on the stairs. You're going through lifts, you're going upstairs, and then there's this really heavy door that they open, and then you just enter this circular room. It's exposed to the cold, crisp mountain air, like your heart is beating fast anyway because there's not much air, but that this is coming to like the big moment. And you look up and there she is in all of her glory, surrounded by this like blue-green metalwork, which is just like the color scheme that they decided to go with for the telescope. And it is this this maze of support struts and platforms. There's none of these neat smooth floors or anything. It's just a jumble of very precisely balanced steel framework, and it floats on a bath of oil, and that's how they get to slew it around so quickly. I think this thing can complete a whole revolution in about a minute. When it's an 8.4 meter mirror, it's seriously impressive. So then you get to kind of go up and actually have a look at the telescope a little bit more closely. So this is a side view of the telescope. You can see some big circular regions, and this is where you can sort of tilt the mirror and then it will spin around and everything as well. And when we went to visit in 2023, they hadn't actually installed the camera yet. So instead, what they had was a dummy camera. So I've zoomed in here on this section on the left picture, and you can see there's sort of something behind this white bit that kind of looks like a camera, but it was actually a dummy camera, so that while one company is building the camera, another company is building the mirrors, they need to still be working on this telescope and get it balanced as near as they can. They can't just wait for everyone to sort of be finished. And so the dummy camera was in there to help them balance the telescope as close as they could before the actual one arrived, just to kind of try and save time. So you've got people working on multiple branches of this all at the same time. And so I've just kind of got a little video here just to kind of try and give a little bit of perspective on how enormous this building really is and what all of the struts look like. Everything is open, it's not fine and refined. It's really raw. And I think it's perhaps not what everyone always expects from a professional observatory. There we go. Where are we? Yes. Then we couldn't go around to this section because they were actually building, but they took our phone and they took some photos for us. This again is a dummy mirror not the actual mirror, so that they can again try and get the counterweights and everything right, try and get the telescope balanced as near as possible before the real one gets inserted. Then afterwards you head outside and you basically just take in all of the views, and I've popped this picture in just to try and give you a scale of sort of how big this building is, because here we are, and here's a 4x4, and this is what the landscape is. So it's perfect in the sense of it's really high up, cloudless skies, you're above much of the atmosphere, and there's a path here down off to another observatory on a hilltop over there. But the Vera C Rubin is not the only telescope at this site. There's also what they call the ancillary telescope. And so this is the view of Vera Rubin from the ancillary telescope, which I've got on the left-hand side. And this is a little miniature telescope, which they use to help them develop this scanning technology. So again, it's all these threads of people working at the same time on construction, on the camera, on balancing. Then people who are developing the software, they need a test bed, and so they've got this small ancillary telescope there, which has helped with the development of that software. And I asked them what it will be used for afterwards, and they're hoping to kind of use it for a bit of outreach and working with schools and things like that. And yeah, that's the Vera Rubin in all of her glory. Of course, she's probably not got the big cranes and stuff outside it now because this was a couple of years ago. But I think it is absolutely extraordinary building. And here we are, 2 years later. We've just had first light. And I thought we'll just finish up by taking a little look at some of those first light pictures. And they kind of hint at the main science goals of Vera Rubin, which are to explore what dark matter and also what dark energy is, which make up most of the universe. It's going to do an inventory of the solar system. So this is finding hundreds of thousands of asteroids, finding 90% of the near-Earth asteroids that could pose a threat to Earth. It's going to map our Milky Way out to greater distances, almost halfway to Andromeda, our nearest neighbour. And then, of course, look at transient objects, so things that change brightness or position. And a lot of the first light images focused on a small part of the Virgo cluster, which is the nearest galaxy group to our own. It's about 54 million light years away. And this is from Tasmania. So I did some sort of screenshots for tomorrow night. If you wanted to have a look at the Virgo cluster, it is low on the horizon from your perspective. But the moon is nearby, just to kind of give you a bit of a guide as to where it is in the sky. And this is about 8 o'clock your time. And you can see some of the brighter galaxies of the Virgo cluster with a small backyard telescope. So like some of the Messiers, 49, 84, 86, which are ellipticals, and then 58 and 61, which are some spirals. And this is Macarian's chain, which is a really iconic part of the Virgo cluster. Now, of course, Vera Rubin's view of the Virgo cluster is quite different. This is the big sort of image of the Virgo cluster. But to actually display this properly, you need 400 Ultra HD TV screens to see all of the detail, which I don't even know what 400 Ultra HD TV screens side by side even looks like. It's so hard to comprehend. And it's because it covers a huge part of the night sky in the snapshot, about 45 full moons altogether, bam, one snapshot. And each snapshot it takes is about 30 seconds, and it does 6 snapshots because it's got 6 color filters, which span from the ultraviolet into the near infrared. Now, this picture they've called the cosmic abundance, which is about 2% of the full Virgo cluster image. So it's the kind of top left section of that big picture we just looked at. And there are a few stars in this picture. You can identify them because they have these diffraction spikes. So the blue and the red here and here. So you can identify those as stars. But every other speck is a galaxy. Everything. So even these tiny, tiny little flecks of light, galaxies, each of them with billions of stars. And in the full Virgo cluster image, there are 10 million galaxies. 10 million galaxies covering about 90 full moons across the sky. And this is just at this early stage. This is just a few hours of exposure, right? So imagine what it's going to do when it's got hundreds of hours behind its belt. And I really like this image. I think it gives a really rich 3D aspect to the night sky. So first of all, you've got these 2 spiral galaxies, right? And they're just like 2 eyes staring out at you, sort of hypnotizing you and drawing you in. And then above them, you see some real violent cosmic drama unfolding, because you've got these galaxies, they're all tangled together, they're pulling on each other, they're spraying out stars in this like yellow mist that's cloaking them all. We don't know who's going to win. Like, we're not going to see that. That's for generations down the road. And then if you look down to the lower left, there's these kind of yellowish blobs all in a line. They're like this little pearlescent choker. And then that's where you start seeing the most exciting stuff, right? Because there's this polka dot background behind this pearl choker. And all of those are galaxies, all those tiny little flecks, right? Especially the red ones. The red ones are the most distant. Their light has taken billions of years, to travel across the universe and finally be collected by the Vera Rubin Observatory. And I really do think that this picture is one of the most moving pictures of the night sky that I have ever seen. It's going to visit each area of the night sky 800 times in 10 years. That means we're going to have 800 snapshots of this patch of sky, which we can turn into a movie. So it's actually going to be giving us a 10-year movie. We can see what happens in every patch of sky over 10 years. And it's not just galaxies, of course. It's finding variable stars. So again, this is the Virgo cluster image where they're just zooming in on different parts. And you can see how sensitive this is because it found an 11% difference in that star over a matter of about 10-15 minutes. There's another one here. Again, what's that? 3/4 of an hour, finding a difference in the variability of the star. And it found dozens of those in the very first image. Overall, it's going to find 100,000 of them, up to 1 million light years away, which is halfway to Andromeda, the nearest galaxy. So it's really going to help us map out the outer edges of the Milky Way and what the space is like in between galaxies. So this is the sort of region that it's going to be exploring, this kind of shell. We've got the main disk of our galaxy and then the halo and then these kind of shell regions, and they've been largely unexplored. So this is what it's really going to start looking at. And in about just 10 hours of looking at the night sky, it found 2,000 new asteroids. 10 hours, 2,000 new asteroids. 7 of them being near-Earth asteroids, but fortunately none of them are dangerous to us. Just for a bit of perspective, all the other telescopes that we have out there, on the ground, in space, all of them find about 20,000 asteroids every year. So every other telescope finds 20,000 over 365 days. And in 10 hours, Vera Rubin found 2,000. 10%. In 10 hours, it found 10% of what all the other telescopes find in a year. That's wild. It's expected to find dozens of interstellar objects as well, like 3i Atlas that's just been discovered. And it will finally put to bed the rumours over, is there a planet 9 out there? So this large planet beyond the orbit of Neptune, out in the Kuiper belt. Because if it's there to be found, Vera Rubin will find it. And then I think the final one is then the Lagoon Nebula. And I think this is a lovely image just to finish on because it's just breathtaking. This is about 700 snapshots that the telescope took over 7 hours or so, and it covers an area of sky about 60 full moons. The lagoon and the Trifid, so this is the lagoon here, front and centre, and then you've got the Trifid up there towards the right. You guys can see this. This is prime time for you guys down in Tasmania to have a look at these objects because they're in Sagittarius, really high in the sky for you right now. And you can see them in binoculars or a small telescope, especially if you've got some dark skies. And so, we're going to get these extraordinarily detailed views of our own galaxy as well. So it's not just about understanding, the universe as a whole, but it's going to give us a really intimate picture of our home as well. And those, of course, are all the things that we know about. It is also going to show us things that we have never imagined. And I think that is a really fitting tribute to a remarkable woman. And that brings me to the end. So thank you very much.
Can you hear me okay, Jenny?
I can, yes. I've just stopped the slides because otherwise I'm going to guys.
Thank you so much for that. I mean, I think we've all been blown away by the images coming out of the Vera Rubin, and to know that it's still in commissioning phase is just astonishing. And I cannot imagine the thrill that it has been to actually go there and see it while it was under construction. It just would have been
honestly
amazing.
One of the best days of my life. Like it's just you just don't get that kind of opportunity very often to see a groundbreaking observatory while it's being built. I feel very lucky to have been able to go out there. But if you do find yourself in Chile and you do want to visit, they do trips. They do like coach loads of people go up and stuff like that. So they are really good about encouraging people to come and see and stuff like that. So if you do, if you are going out there for whatever reason, give them an email. The worst that happens is they say no.
Yeah. No, fantastic. Now, I know we've gone a little bit over time, but we might just do a couple of audience questions. Have you got time for that?
Yeah, so, absolutely.
Yeah. All right. We'll just see who's got some questions I'll pass you over to our first question from Steve.
Hello, and thank you for the presentation. Immensely, thank you. I presume this is a multinational exercise. There's a list of countries that have contributed to this, are there, or the space agencies from Europe and so on? Well, what's the list?
Yes, I don't know the full list, but yeah, it is a multinational effort, as most of the observatories are these days, because they just cost so much money that you can't kind of do it with one nation alone. I know that America is definitely involved, but I'm not sure what the full list is. But it's a great question, and they'll definitely have it on the website. There'll be a full list of affiliations. But yeah, ESA will be involved.
Maybe one last question from Robin.
Hi Jenny, how are you?
Good, thanks.
That's great. So my question is, and I don't want to be greedy, but we've had Hubble, we've had James Webb, now we have Vera. What's next?
Oh, I like this question. Okay,
not that we're finished with any of them yet, but...
So in terms of ground-based, there are things like the 30-metre telescope, which Trump has threatened to pull out of, and then Spain has now gone, well, that's fine, we'll buy it off you. So that's, I think it's Hawaii. So that would be a 30 diameter meter. So the Vera Rubin's 8.4, and then that one would be 30 meters. Then there's like the extremely large telescope, which I think is about 25 meters, something like that. So these are like ground-based. So those are either early stages of construction or kind of finishing conception. They are not going to come online for at least a decade. So they are very much the next generation. In terms of space-based telescopes, there is a concept called LUVOIR, which is the Large Ultraviolet Optical Infrared Telescope, which is if you take Hubble and James Webb and like made them have a gigantic baby, that is what it would be. So imagine it's like the structure of James Webb, where you've got this big hexagonal mirror and the three struts and everything. But able to see ultraviolet and optical and infrared, which is what Hubble can do. So Hubble spans all of those wavelengths. So that's the kind of next conception for a massive space telescope. But that wouldn't be till 2040s, something like that. So yeah, those are the kind of big next massive projects.
Yeah, fantastic. Jenny, just before I hand you over to Ross to wrap things up, what advice would you give to a young person that is interested in a career in science or astrophysics?
So I think for astrophysics, you do need maths. So you need to follow maths at school, because I know it's not everyone's like favourite subject, but that's quite often because the teachers aren't brilliant rather than necessarily they hate maths. Pick up some computer skills if you can. When I say you need maths, it's not, don't worry if you find maths tricky, because the thing is, all computers do our maths for us now. So you just need to be able to understand the concepts, and the computers will actually do the computing for you, as it were. I would say, don't worry about having lots of astronomy and astrophysics knowledge until you go to university, because it'll all be taught to you at the university. So you don't need to go in with bags of knowledge. And I would say it's a really good career to follow because you will never be out of a job. You are taught so much in terms of like data analysis and data processing, how to handle complicated data sets. Because I'm telling you, if you can deal with a galaxy that's throwing a wobbly at you every time you try and look at it, you can definitely deal with data that's to do with people. So you'll always have job potentials and stuff like that. It's hard, it is difficult, but it's super fun. And there are lots of avenues to go into that's not just in the university in terms of astronomy. You can do outreach, you can do kind of journalism with it as well. And these are things I didn't realise when I was sort of going into it. There's all sorts of things related to astronomy. So yeah, I would say maths, some computer skills, because we do everything with computers. AI is becoming huge in astronomy now. So I would definitely try and pick up some AI and machine learning skills and things like that. But yeah, it's good fun. I wouldn't change it. I love my job.
Okay, thanks, Jenny. So tonight you've taken us all on a fascinating journey from the Big Bang all the way through to the launch of the Vera Rubin Observatory, all the science, and importantly also the history that was behind all the science. And then you took us back almost to the beginning of to the Big Bang with those beautiful visions of the galaxies. And talking about galaxies, I'm also a big fan of the Galaxy song. And present company excluded, we're still searching for intelligent life on Earth. So, if anyone has not heard the Galaxy song, please listen to it. Thank you very much. If you're ever in Australia, please come down to Tasmania. You've made a lot of friends tonight. And please, everyone, show your appreciation to Dr. Jenifer.
Well, I'm hoping to be down for the eclipse in 2028.
Okay, we look forward to it.
So.
Okay. All right. Thank you very much. Good night.
Bye. Thank you so much for having me. It's been great fun.
Okay.